In case you haven't heard about so-called Moore's law, here's the gist about it. It was first formulated by Gordon Moore, who in 1965 have noticed that the density of transistor packaged on integrated circuits, or short ICs, grows roughly by a factor of 2 every year. In 1975, he adjusted his forecast and claimed doubling of density every 2 years instead. And so far his projection has been true, at least until the year 2010. Since then the growth slowed down a bit again, but we still had more or less exponential growth of transistor count at least until 2019. And the outcome of that growth is that we now have integrated circuits that have 50 billion transistors on them compared to a few thousand of transistors in 1970s. This means we can in theory put some 50 million Motorola 6800 cores, which were only a few thousand of transistors in size, in a single crystal, and we will have a 50 million core processor. That is probably not the best solution though, because those processors were very limited in their functionality, but we have the technology to do this. The growth of computational power due to the increase in the amount of transistors still drives creation of new devices today. But this progress was not without hiccups. The biggest one happened between 2005 and 2010, when the reduction of transistor size stopped giving us the opportunity to increase also processor clocking speed. That famous gigahertz that you hear about in marketing materials. This resulted in significant slowdown in growth rate for applications that could only use a single processor core at a time. As a response to that, two things started happening in the research labs. First, we have started implementing things like instruction-level parallelism, where your code will no longer be executed strictly sequentially, but instead processor will decide which commands of your code can be executed at the same time. This let us squeeze about 6 times more instructions executed per each processor clock, from typical 2 clocks per instruction in 2005 to almost 3 instructions per clock executed on average nowadays. But this path causes a lot of extra complexity, and we're almost at the limit of going further this way. This also has resulted in a few hardware-level vulnerabilities that you probably have heard about, such as Spectre and Meltdown, and a few other names implementing the same strategy, that is, attacking the hardware designed to parallelize execution in order to gain illegal access to protected information of other programs that are running on the same physical core. The second approach is that we started the process of adding extra cores on the same processor chip. Unfortunately, it is easy to say just copy the same processor 50 million times, but in reality, a lot of synchronization problems occur because cores have shared access to caches, memory, and other resources, and extremely limited ability to communicate between each other actually. So we were able to fit in 2 processors, then 4, then 8, and nowadays complex server processors have up to 64 cores, in the case of x86 architecture, and even 384 cores for much more compact ARM cores. Unfortunately, this change also meant that the software we use have to be adjusted. And in this lecture I will present you how you can do this in Python. Let's have a look at the example problems that have been presented in exercise 1. Here we have a small example of the problem that we have already solved during the exercise 1, and this is the exact solution that have been presented, with the only difference that I have taken all the functions that we have implemented to solve train meet problem and put them into a separate module. I basically copy-pasted them here inside the train spy and added import math module, which is required for this module to function. And now, using this simple modification, it was possible to just import the solve train meet and get city to city distance functions from the trains module, so that we can use them in this part. What we're going to do here. So we now have the solution for this problem, and you can see that it works. If we just execute every cell one by one, we will get exactly the same results, minus the intermediate printouts, which I commented out here in the train spy. These prints are commented out, so we no longer get this intermediate information because it was basically necessary for debugging and testing of our code. But now that we know that it works, it's no longer necessary. And what we're going to do here, we're going to modify this part too, so that the code can be then turned into parallel form. But first we need to add a small modification here. We need to add the calculation of distance, because part of the problem that is in your home assignment is calculation of distance for this problem. And the distance is to be computed from the intersection point, the midpoint, the mid coordinates, to some arbitrary specified target coordinates. So let's first start with those. And now let's also add calculation for those coordinates. Okay, now we computed the distance. In addition to our mid coordinates, we can use the same function that we used to compute the distance between cities, because the equation would be the same. And now we need to store not only mid coordinates, but also the distance. So to do that, we are going to use a list created right here. Okay, now that we have this new list that has first element set to mid coordinates and the second one set to distance, we can rerun this code and check that it works. And as you can see, everything goes fine here. So for every combination of initial speed for train A and train B, we get mid coordinates and the distance from the selected target point. Okay, this is good. Now that we have all the modifications that are necessary for the main code, let's do the refactoring necessary to make this code run in parallel. The first step that we will need to implement is preparation of arguments. So we now have these two iterations for speed of train A and speed of train B. And from there we create this list of arguments that is passed into our solve train mid problem. So we will refactor that, and we will first create a new block here. Here we're creating a list call arguments, and we are going to iterate through the same two ranges for train speed A and train speed B. And we are going to populate the list in more or less exactly the same way as we had in the call to our solve train mid function. The only difference here is that we also added target as a last argument, because we want to pass this target explicitly to whatever computations we're going to handle. This is one important notice. Whenever you are doing parallel computations, you have to pass everything explicitly, otherwise you will basically lose data, because global variables are not guaranteed to be transferred anywhere. In some cases it might work, but that would be more of an accident rather than an actual planned working situation. Okay, now that we have this reworking done, we will have list call arguments that will contain all the arguments that we would like to pass into our function. Now let's prepare the actual solvers. In our case, we are going to use a function, and we will name it runSolver. And in this function, we are going to first unpack all the variables that we have passed into the call argument list into individual values, and we will preserve their names during unpacking. And then we're going to take our mid time and mid coordinates computed by solve train mid function. This solve train mid function is unchanged, so we pass the same arguments to it, and the target is not used there. Instead, target is used on the next line here, where distance is computed by get city to city distance. And here we pass mid coordinates that were computed in the previous step, and the target that has been passed as argument. The result of this computation is exactly the same as we had here. So the list that has first element set to mid coordinates and the second element set to distance. And we would like to return this list from this runSolver function. Okay, now we have the list of arguments prepared and the function that will actually do the solving. Let's use these two together to actually compute some results. To do that, we are going to first prepare the list that will contain the final results, and we are going to have argument set variable as our iterator variable that will go through every value in the call arguments list, and we will pass this argument set to our runSolver function using this variable and this call, and we will take the processed results, this list, and store it in the processed results variable. And we have a small typo here. This of course has to be two different variables. So we're going to have a single result here, and multiple results as list. And we are going to save this, and we're going to append processed result into this list. Okay, now we no longer need this part at all. And after we have implemented this, our function will actually iterate through all arguments possible that we have created, and it will compute the results and store them. So let's preview how it looks like. Okay, as you can see, we now have a list that has just mid coordinates and distances, but no reference to the original speed of train A or train B or other arguments. So in order to fix that, we will need to do a little bit of post-processing of our calculations. So let's add another post-processing block. Here we are going to zip together two lists, the original call arguments and processed results list. Because this one was processed sequentially, the order between processed results and call arguments is the same. So 0 element in call arguments corresponds to 0 element of processed results, element 1 corresponds to element 1, and so on. Then we are going to iterate these two together as a single larger list or iterator. And in every pair, we are going to assign the first value to argument set and the second value to result set. This is similar to what we have here, but instead of iterating just one value, we are iterating two at the same time. Now we can unpack our argument set into the variables that are stored there, and we can unpack our result set into the variables that are stored there. So that is mid coordinates and distance. And if we have our check for train speed in the final dictionary that we create here, the results dictionary, and if this check does not pass, which means that train A speed has not been initialized yet, we are creating a new dictionary for that. And then we're using this construct to create effectively a dictionary of dictionaries, where first key is speed of train A, and the second key is speed of train B, and the value is assigned to this element mid coordinates and distance. And this is exactly the same format except for the distance that we have been getting before. Now if we run this and restore our previous version of results, we can see that all mid results contains proper values that we expect, though keys for train A, keys for train B, and the finally calculated mid coordinates and distance. So what is important to understand about this code is that we have now decoupled three different parts. The first part is preparation of arguments. So whatever happens before we call our calculation is now completely decoupled here. And all the processes that are necessary to be performed, for example, queries to databases, some kind of analysis, in our case iteration over ranges, these are all completed in a single threaded manner. This is normal. And usually these processes are quite fast because they are not actually involving any heavy computation. Then the second part, described by these two blocks, is the part that relates to the actual computation of our problem. So this function implements a solution, and this function is a generalized way in which we can pass all possible combinations of arguments to our solver function and get all answers that we need for this set of arguments. Essentially, it doesn't matter how large this call arguments list is, so we can later freely modify these ranges, for example, and increment the amount of points that we are analyzing, and the rest of the code will still work. And this helps us to think about this process independently. So again, first we have preparation of arguments, and then second step, we are doing the actual calculation, and this is a generalized form. And we specified by providing this run solver function, which implements the actual calculation. So this function is what does heavy lifting. In our case, we also have this embedded solve train meet call that will also do some heavy lifting inside of it. But in general, this run solver is like the upper level of wrapper above our calculations that turns our input argument set into the results that we request. And finally, we have post-processing. The post-processing part also happens in a linear serial way, and there is no need to parallelize it in most cases, although in some cases it is possible to do so if there is no aggregation involved, for example. However, The important part is that now this function, it can be parallelized without any limitations in principle, because all arguments are independent. There will be no change in arguments to one of the call based on the results of previous executions. And all the results are also independent, and they can be stored in the list and then later post-processed in a fast way that doesn't involve any excessive intensive computations. As you can see, one of the key parts here is that we have these two iterations, because these two allow us to create a lot of uniformly looking sets of arguments. If, for example, train B speed was somehow dependent on previous calculations, then it would have been completely impossible to do this way. But in most physical problems, in most of analysis that you will be running in your real life cases, this is literally how it looks like. You will have different parameters, and you will have minimal and maximal range, and then you will have steps in which you are going to test those models. And then you are going to take the result, plot it maybe, and see where is minimum, where is maximum, where is some interesting behavior, maybe change ranges, maybe increase density in some places. But other than that, this is the template for any sensitivity analysis that you might need. All you need to do is just specify your list of arguments, maybe by increasing the amount of loops here, changing the ranges, changing the way you format the arguments, so you can modify. In this case, we have 1, 2, 3, 4 constant arguments which don't change their values in the loop, but you might have multiple arguments dependent on the same loop variable, and so on. And then you run the solver, and this is the generalized form, and you only need to modify your run solver function to implement your actual calculations that will take your actual list of arguments and compute something that you need. And finally, you do post-processing. In this case, we're doing a very simple one, but you might actually implement the plotting or statistical analysis in the future for post-processing your results to present them in some way that will be understandable for human and not just this mess. And before we continue using this code in the future parts of this lecture, let's do a few minor tunings here. First of all, we don't really need to unpack this list. We can use this argument set variable and pass it as a variable argument list. So we can use asterisk syntax. And the only problem is that we now have target at the end, so we have more arguments that we need. But we can slice this list before we unpack it and pass it into the function using this slice operation. So our start is at the beginning and our end is at -1 element from the end. Then we don't need to pass target here, and we will not be able to pass that once we delete this line. Instead, we need to just pass argument set -1, and this is the same as target. And now we can delete this unpacking to save one line and a lot of text. Then at this step, we are having this extra variable. We really don't need it. We can just copy paste this part and plug it into the append directly. And this will work as intended.